inside the ears at high pressures, but later we realized that it has much broader application range. We can explore the matter at extreme condition, we can design new materials, we can search for metastable structure, and it can be quite important if you want. Sometimes you can find some very interesting metastable structure and quench it to ambient condition. And we also can test the theoretical approximations. And the main computational obstacle, as Artem already told you, is the search space. Because even if you have relatively small amount of atoms, the search space is huge, and there is no way that we can do it with a classical computer. We cannot search it explicitly. The only possible way would be, of course, quantum computing, but there are no quantum computers, and there will be no quantum computers in the nearest future. That's why we have to think about empirical methods that give results good and quite often, so that have high success rate. And one of the key features of our method and all current methods that deal with crystal structure predictions is local optimization. The search space, for example, the energy surface, is extremely noisy and huge. However, we can sort of smooth it and reduce the effective number of degrees of freedom by a lot if we do a local optimization. This way, the landscape is much smoother, and sometimes, our calculations show that the amount of degrees of freedom, the effective amount of degrees of freedom, can be lowered by 2 or 3 times, and that's a lot. And this step, this local optimization step, is actually the most computationally expensive step in our calculations. All these evolutionary operators and all this quite fancy and complicated stuff that we are programming can be done quite fast, but this is our bottleneck, the local optimization. Till recently, we were using just a few codes, WASP, CIEST, and GULP, but now we are starting to expand, and actually if users want us to, for example, include their code or include some code that they are using, it's usually quite easy to do because USPECH is sort of higher level program, and it uses the results of this program and actually relies on them. So if the physics is not correctly represented by this code, of course our results are not good. So we rely on this code, and actually all we need to start the calculation is the chemical formula, number of formula units in the unit cell, and the condition. That's it. And we can start. We don't need experimental results, but of course they help us, and we can incorporate them into the input to make the search faster. This method has been in development since 2006, and we achieved, we and our collaboration, a lot of interesting results. We found many new crystal structures, and some of them Artem presented you were quite excited, like sodium or boron. I'll concentrate more on computational part. So each average calculation, usually we have to locally optimize from 500 to 3,000 structures. Sometimes it's more, and sometimes for a simple system it's few, but it's something in this range. And each local optimization consists of a few local optimization steps. It can be 5, it can be 7 steps. And as you can see, we have relatively cheap steps. So one optimization can be done, for example, in a few minutes or in a few hours, and only in very, very complicated cases it is more like a day. However, we have a lot of such small steps. This allows us high parallelization. For example, if we have a population of 20 structure, we can actually just submit 20 jobs, and that's it. However, there are some requirements for hardware. First of all, we need small waiting time and ability to launch many jobs at one time. And the third, it can sound quite strange, but we need the facility that supports small job sizes, because we encountered a really strange situation when we started to work with Blue Gene in Stony Brook. when you submit a job, it allocates you at the very minimum 512 processor, even if you do like 8 processor jobs, and the rest is wasted, and actually, well, they count as those processors as used by you, and we had to use some mechanisms that were experimental and not used before, like some special reservation and special job submission to be able to use all the processors from this, for example, 512 processor cluster. And then we realized that the number of the jobs that we can submit is also very limited, because the supercomputer was sort of designed for very big jobs, and they didn't want people to completely fill it with jobs. So you can submit only like 6 jobs from your account at one time. So they had to raise us the amount of jobs we can submit, and we have to use fancy methods to submit them to use the processor efficiently. And also, waiting time can be crucial. If we are waiting 2 hours and then calculating, making relaxation within 1 hour, then it means that actually 66% of the time we are just waiting and doing nothing. And in some supercomputers, and our BlueGene is not an exception, small jobs actually have longer waiting time than big jobs. Usually they allocate a big amount of processors, like 5,000, for example, to those big jobs, and we just get the leftovers. And our small jobs wait for these leftovers. But anyway, this is what we would like to have from a hardware point of view. Now, what we can do and what we cannot do. As you already know, we cannot guarantee a global minimum, and no method can, actually, but we have quite a high success rate. Also, now we cannot study very large systems, so we are limited to something like 100 atoms, but it's already much better than it was, for example, 4 years ago. And we cannot give realistic predictions if the level of theory that we use to make local optimization is not valid. And what we can do, well, we can find the global minimum with quite a high success rate for relatively small unit cells. We can find many low energy metastable states, and then you can check if they are quenchable, if they have some interesting properties. In principle, we can also work with finite temperature, and this method is highly parallelizable. So we can use 5,000 processors for one calculation without a problem. We just make many structures in the population, and well, we can really use a lot of processors. Now we have a lot of work, and actually we have more ideas that we can implement by ourselves. First direction is to extend the method to large systems. It's really hard because the complexity of the task rises exponentially with the number of atoms in the unit cell, but we have found some interesting ideas like really smart mutations that exploit the chemical knowledge that we know about the system. There are some things in this highly multidimensional surface properties that help us a lot to reduce the effective dimensionality of the problem. We also use some abstract fingerprint space that put us a matrix that helps us to distinguish different structure and speeds up the calculations. Another directions are multi-component systems, where we can predict both stoichiometry and structure. Artem showed you the results of Lennard-Jones calculation, and we can simultaneously predict a convex hull. And it's also very important because it saves you a lot of time. You don't have to check every possible composition. And sometimes you don't even try to check some compositions that surprisingly are stable, like this A14B. Third direction is optimization of some other properties and structures. For example, we now have an algorithm that allows us to search for the hardest phase. It's not always the stablest phase, but it will give us insight about hardness. And sometimes you may think if you can quench it, for example, like a diamond, and make it stable at normal conditions. You can also optimize the electrical properties, volume, and if someone approaches us and says, hey, I would like to optimize some other property and I know how to calculate it quite fast, it's not a problem. We can incorporate it into our algorithm. We also want to try beyond DFT levels of theory, some quantum Monte Carlo. It's even more parallelizable and allow us to use these Blue Gene computers where they have many relatively cheap and not very fast, but a huge amount of processors. So you can use like 10,000 processors at one time. And the newest field of development are clusters, surfaces, and interfaces. So we predict the clusters at given conditions, the surfaces, and well, we have some really interesting result, but we need more manpower because in the last year, our code actually doubled in size, and there are only 2 people, myself and one of the PhD students that are working on it. And well, of course, we need financial computational resources, but the biggest need are people, young people who are good both in software engineering and in physics and chemistry. That's why I told yesterday that it's important to prepare such people and give physics lecture to computational scientists and some IT lectures to physicists. And I also would like to thank my collaborators and people who are working with us on developing the USPECH. Thank you very much.
What do you mean by finite temperature when you say you can do it at finite temperature?
Well, we mean that we can use this, well, usually we do calculation for t equals 0 because it's faster, but WASP and some other codes allows us in principle to do finite temperature calculation because people always complained earlier that all the results that we present are done at 0K, but it's not like USPECH or our method limitation. It's just limitation of those codes. And as soon as we have a code that does this calculation quite fast for the limit, well, for non-zero temperature, then we can just use it and that's it.
Oh,
so our code is...
If you had a code that could tell you free energies instead of zero temperature energies,
yes.
you could do finite temperature.
Mm-hmm.